Yeah, hello everyone. Welcome to the new series of this project. So I'm here to help you to understand this project, which is Embryo Quality Prediction using ERA. Before start this project discussion, let me quickly introduce myself. I am Buddhabhushan Chakre. I'm Associate Data Scientist at AiSPRY, and today I'm here to explain this project. So as a 360DMG, as a AiSPRY, whenever we work on any project, at that time we follow crisp MLQ methodology. Okay, where we have a 6 phases. First, which is business understanding and data understanding. Second, which is data preparation. Third one, which is model building. Fourth, model evaluation. Fifth, model deployment. And sixth one, which is monitoring and maintenance. So whenever you work on any project, at that time we need to follow this methodology, which is crisp MLQ methodology. And here, while working on this project, we understand the problem first. For that, we have a business problem. So here, endometrium receptivity analysis, which is ERA, is a molecular diagnosis test, which is used in IVF, which is in vitro fertilization, which is help us to determine the optimal window of implantation for an embryo. Because, like, see, the thing is, now in normal way, in IVF, basically we take a sperm from male, oocyte from female, we fertilize outside, and which will form an embryo. And sometimes when embryo implanted into the woman's womb, at that time it will not grow properly. So for that purpose, we need to find out the optimal window. Okay, optimal window of the implantation. We can find out that with the help of endometrial receptivity assay. So many IVF failure occur, okay, due to embryo transfer timing, which is not aligned with the endometrium receptivity. And the traditional methods rely on the general estimation and leading to implantation failure, as I told, and reduce the pregnancy success rate. By using ERA, clinicians can personalize embryo transfer timing based on an individual endometrial gene expression profile and increase the chances of successful implantation. Means, like, if in normal way is not once we form the embryo, and if the embryo is which is not growing inside the woman's womb, at that time women face a lot of issues, right? Pregnancy, woman's like womb is not growing inside a woman's womb. So first of all, we need to understand whether the endometrium is receptive or not. So for that purpose, we need to consider ERA. So this is the business problem. And while working on this business problem, we understand the objective, business objective, which is maximize, improve IVF success rate using ERA. Because in normal way, so whenever someone go for the IVF, which is quite expensive. So, and along with that, we just want to improve the or maximize the IVF success rate. So this is the business objective that we have. And the business constraint which we have, which is minimize the diagnostic cost, minimize the additional diagnosis cost while ensuring the accuracy of receptivity prediction. So basically, whenever, like as I told earlier, whenever someone goes through IVF, it is costly. So we are trying to minimize the diagnostic cost using a ERA, which is endometrial receptivity array, basically, which will help us to identify the receptivity. And along with that, we are having the 3 success criteria, which is first one, business success criteria, which increase the implantation success rate by at least 20%. Okay. By aligning a embryo transfer within the with the receptivity window. Basically, we just want to improve the IVF success rate by at least 20%. Along with that, we are having a machine learning success criteria, which will help us to achieve a predictive accuracy of over 85% in the identifying the optimal implantation window using endometrial gene expression data. So, and this is the this is the machine learning criteria. We are trying to achieve the accuracy more than 85% while work on this project. And along with that, economic success criteria, where we consider the reduce the IVF cycle failure by at least 30% and leading to the cost saving for the patients and clinics by avoiding unnecessary embryo transfer. So this is the thing. So we work on that. Along with that, as you can see here, we are having the architecture diagram. Basically, you can see that we are taking data from the multiple sources. Then we load into the Python. Then we perform a data preparation, and then we load the data into S3. Then we perform a model building. And once we build the model, then we evaluate that with multiple architecture, with multiple architecture. And once we get the desirable accuracy, then we deploy that with the help of Streamlit and AWS. And after that, we need to maintain and monitor that so that it will work good with a good accuracy. So this is thing. Along with that, we use a multiple kind of data. Basically, in data collection, we use a image data. Basically, we use a image data. Okay, and multiple patient data. Basically, we use a metadata and image data where we consider a demographic features like age, body mass index, and patient ID. Along with that, we consider the hormone levels like progesterone level, estrogen level, AMH, FSH, LH, and we try to understand that whether the implantation is successful or not. And as I told, we use a image data with a metadata, which is a graphical tabular data. We use a ultrasound images of the endometrium. We segment that. We split the data first into three parts: trend, test, and validity. And based on that, we perform different pre-processing techniques. Along with that, as I told, we use a different kinds of data, like we use ultrasound images and the grayscale images. And our goal was to segment the data, segment the image and classify whether it's good or bad. Okay. While performing that, we use the images and we perform different pre-processing techniques like augmentation and all. While performing the augmentation, we use a flip, rotation, normalization, and many more things. Along with that, we consider, as I told, we consider the different pre-processing techniques. We understand in the clinical data or the metadata, we are having any kind of missing values or what. If we are missing, as of now, while doing on this project, at that time, there was no missing value. So yeah. Along with that, we split the data into three portions: train, test, and valid. So with the help of that, we try to build a model. Along with that, while performing the pre-processing, we use a scaling and normalization technique. And as I told, we use a tabular data. For the tabular data, if any categorical data is there, then we transform that. And we use multiple features along with that. As I told, we use this kind of techniques like data organizing, resizing, augmentation, normalization, conversions, those things that we perform. And we use while doing a model, okay, while working on the model building, we use a multiple models. For the segmentation, we use unit, okay, deep lab v3. For the classification purpose, we use classification different models. We use a optimizer as Adam, loss function as binary, cross entropy with a Dias loss. Okay, we along with that we use a fusion models so that it will combine a clinical data, metadata, and image data so that it will work fine. And when we combine or fuse the model, then we use a different evaluation metrics such as accuracy, precision, recall, F1 score, AOC, ROC. And for the segmentation model, we use the Dias score, IOU. And for the classification, we use accuracy, F1 score. And these are the comparison of model accuracy. We, as I told, we use multiple models like light GBM, sorry, GBM, yeah, Tabnet, MLP, UNet, FPN, Deep Lab v3. Those kinds of models that we use, and those are the accuracy that we find out while working on the project. And we find out for the clinical data, those are the different models that we use, and among the all, whichever the model that gives us the good accuracy, like light GBM, we use that for the clinical data, and for the image data, we use UNet, and for the fusion, we use a logistic regression with a random forest, not with or random forest with XGBoost. So whichever the model that gives us the good accuracy, we use that for the best model. And these are the screenshot that we can see here. Okay, as you can see here, uh, this is the Streamlit application images, the photo, where you can see here we mention the patient data over here, like what is the age of the particular patient, body mass index, progesterone level, estrogen level, AMH, FSH, those things. Along with that, we correlate those tabular features with our image data. And once we upload the image, then as you can see, this was the original image, and this is our classified image, that green line that you are seeing here, which is the important part of endometrium. And based on that, as you can see, it shows the end quality of the endometrium, which is good, and the endometrium thickness, which is, as you can see here on the screen, and the metadata, probability and all, as you can see, and the patient log. So this is the thing that we need to understand. So basically we try to use clinical data or tabular data where we use a multiple features like body mass index, age, progesterone level, estrogen level, AMH levels, along with that LH levels as well. And along with that, we use the endometrium thickness, endometrium volume, so that we can correlate our image with our inputs. And based on that, it gives us the classification and segmentation. Yeah, this is the thing. And if you have any question or any concern, you can ask me. Otherwise, we can wind up for this day. Yeah, that's it from my end. Thank you. Thank you for your time.